Okay, picture this. You're staring at a massive spreadsheet, just a total sea of raw numbers, and you're feeling completely lost. We've all been there, right? But what if I told you that you could instantly interpret all that complex data just by recognizing a few basic visual shapes? Well, let's dive right into this. Welcome to our ultimate visual study guide, where we're going to transform those dense statistical formulas into clear, memorable visuals. Welcome to today's explainer. Think of this session as a high-energy, interactive mental flashcard round. Our main goal here is to completely decode statistical reality using only the raw materials and data we're putting right in front of you. No fluff, just the absolute core concepts you need to know, mapped out visually. So here's the mind map for today's session. We've got 5 key checkpoints to hit. First, the basics of data. Second, visualizing trends and associations. Third, measuring central tendency. Fourth, the rules of probability. And finally, number 5, random variables and distributions. All right, let's kick things off with Section 1, the basics of data. This is where we lay down the foundational building blocks for literally all of statistics. Ready for your first mental flashcard? Let's test that active recall. When we look at raw data, how do we fundamentally categorize when it was collected? Like, what's the actual defining difference between cross-sectional data and time series data? Lock an answer in your head. And let's flip the flashcard. So the key separator here is just time. Cross-sectional data is collected at a single, frozen point in time. It's like snapping a photograph. Time series data, on the other hand, is collected over a period of time. Think of it more like recording a video. It captures the flow and all the changes happening across days, or months, or even years. Now, beyond just time, we also group data by measurement scales. Categorical data uses the nominal scale for simple named categories, and the ordinal scale for categories that have a specific order. But the real magic happens on the numerical side. You've got interval scales, which are numeric but don't have a true absolute zero. And then you have ratio scales. Now, this is crucial, because ratio scales possess an absolute zero, like when you measure temperature in Kelvin or count physical objects. They actually unlock the ability to do full mathematical arithmetic. It's a real game changer for data analysis. Okay, moving right along to Section 2, visualizing trends and associations. This is where we take those raw categories and ratios and translate them into actual visual stories.
So, if you want to spot a trend, you need a map. And in statistics, that map is the scatter plot. Now, the rules for this visual map are pretty strict. Your horizontal x-axis, that holds your explanatory or independent variable. Your vertical y-axis holds the responsive or dependent variable. The whole point of plotting these dots together is to get instant visual insight about their association. We're asking, does the x-axis drive the y-axis? Like, do the hours you study independently drive your dependent test score? A scatterplot takes that invisible relationship and puts it right in front of your eyes.
But, just seeing a trend isn't quite enough. We have to be able to measure it. So, time for another flashcard. If we see a clear line forming in our scatterplot, what mathematical tool do we actually use to measure exactly how strong that linear association is? The answer? Correlation. Specifically, the Pearson correlation, which we denote with the little letter r. Notice how visualizing a simple line completely strips away the fear of the intimidating math formulas behind it. It reveals a really simple reality. Correlation has a strict, unbreakable range from -1 to +1. -1 means you have a perfectly strong negative association, +1 is a perfectly strong positive association, and right dead in the middle at 0, that means the association is totally weak. Also, a quick pro tip, the correlation coefficient literally has no units. It is purely a measure of strength. Awesome. Let's hit the next branch of our mind map, Section 3, measuring central tendency. Because how do we take a totally chaotic scatterplot full of hundreds of data points and boil it down to a single representative number? Well, we use the big 3, mean, median, and mode. The mean is your classic average, we all know that one. The mode is just the most frequently occurring value in your set, but pay really close attention to the median. Yes, it's the exact middle value, but calculating it requires a super important first step. Your list of data absolutely must be ordered first. If your total number of observations, n, is odd, it's the exact middle number. If n is even, you just take the average of the two numbers right in the middle. Simple as that. Now, if you really want to grasp the full shape of your numerical data, you pull out the ultimate cheat sheet, the 5-number summary. This breaks everything down into 5 clear milestones. You've got the minimum.
then the lower quartile, or Q1, the median, which is Q2, the upper quartile, Q3, and finally, the maximum. This structure is brilliant because it literally shows you how your data spreads out. And if you ever need to find the interquartile range, the IQR, you just take Q3 and subtract Q1. Boom, done.
Let's shift gears now into Section 4, the rules of probability. We're moving from summarizing data to exploring the absolute fundamental rules of chance. All right, here's the classic mix-up for our next mental flashcard: permutation versus combination. The difference between these two literally comes down to one single word: order. A permutation is the ordered arrangement of objects. The exact sequence is absolutely vital. A combination, on the other hand, is just selecting objects from a group where the order doesn't matter at all. To ground these sort of abstract concepts in reality, just think about a standard deck of playing cards. You've got the whole shebang, 52 total cards, split perfectly into 26 black and 26 red, and then further divided into 4 suits of 13 cards each: clubs, spades, hearts, and diamonds. Calculating the odds of drawing a specific poker hand, that relies entirely on combinations. Why? Because holding a hand of cards doesn't depend on the order you drew them from the deck. It just depends on the final group of cards you're actually holding in your hand. And keep in mind, all of these card tricks and probability calculations have to operate within the strict boundaries of axiomatic probability. The rules here are absolute. The probability of any event must always be a fraction between 0 and 1. You can't have a 120% chance of something happening. And if events are mutually exclusive, meaning, say, you can't simultaneously draw a single card that is both entirely red and entirely black, you just add their individual probabilities together. Honestly, whether you're using the multiplication rule or getting into Bayes' rule, these core axioms are totally unbreakable. And here we are at our final checkpoint, Section 5, Random Variables and Distributions. This is where the magic happens, where random chance and visual associations merge into predictive mathematical shapes. First, let's just quickly demystify a term that sounds way scarier than it actually is. A random variable is literally just assigning a numerical value to an outcome. That's it. It's a real-valued function defined on your sample space. If you're counting something specific, like the number of cars passing by, it's a discrete random variable. But if it involves measurements that can take any value within a range, like measuring exact time or weight, it's a continuous random variable. Let's test your visual intuition here with a quick mini pop quiz. If a continuous random variable plots a visual shape, what does a distribution curve actually look like when the data leans heavily to one side? Do you happen to know what we call the long trailing end of that curve? Check this out. Notice that if your data pushes the main bulk, the mass, over to the left, it creates this long tail that gets pulled out to the right. We actually call this right-skewed or positively skewed. And conversely, if the tail is pulling out to the left, it is left-skewed or negatively skewed. The trick here is that the naming convention always follows the tail, not the tall peak. And then, sitting perfectly right in the middle, you have a beautiful, symmetric distribution. And honestly, this brilliantly illustrates one of the absolute coolest phenomena in statistics, especially when we look at binomial distributions. A binomial random variable deals with independent, identically distributed trials. Think about flipping a coin, where landing on heads is your probability of success, P. When your sample size n is really small, the distribution can easily end up heavily skewed left or right, depending on what p is. But notice what happens as n gets large. Regardless of that initial skew, the shape magically starts approaching perfect symmetry. It's like the chaos of pure randomness naturally organizes itself into total predictability. It's amazing. So we've gone from the very raw basics of cross-sectional data all the way to predicting the visual shapes of complex binomial distributions. By relying on these visual maps, scatter plots, and 5-number summaries, the invisible, confusing rules of statistics become completely tangible. To wrap up our explainer today, I want to leave you with this thought. If a simple curve on a graph can reveal the hidden laws governing random chance, what other invisible trends might the everyday data in your own life be hiding? Keep your eyes open and keep mapping it out.